Okay, online.
Okay, so good afternoon, everyone. Thank you for coming for the second lecture. So I wrote here a summary for the first one. This is the what you should remember from the first one, where we were very slow and we just rephrased known concepts of symmetry in a slightly unusual language. So we said that a theory has a symmetry group G, and G can be anything. We did U1 in quite some detail, and then we also showed an example where G was a discrete group, finite group Z2. And the way to characterize a symmetry in general can be done in two equivalent ways. Either you can say that you can couple the theory with background gauge fields, B. So B is a one-form background gauge field, and it is subject to gauge symmetry. So B1, if you have B or B plus D lambda, these are equivalent background gauge fields. That's a symmetry that acts on a coupled theory, where you couple your initial theory with that. It can be coupled in such a way that the partition function is invariant under the gauge symmetry. And the other characterization we derive that this implies the other one is that there exist topological operators, UG of sigma G minus 1. So the operators are topological, which means that you can basically move them around as long as you don't cross operator insertions and so on. And they give the same result in the inside correlation function. And these operators are defined on codimension 1, so dimension D minus 1 if we're in D dimensions. As on codimension 1 manifolds, you can define those operators and for each element of the group. And when you merge them, when they obey the group. So that was the thing. And we also, so we argued that one implies the other, and conversely, the converse provided like these background gauges were flat, but okay, let's not go into this. I just want to make some more comments about this before we start with the new thing. So today, we will, at last, we will go beyond this standard definition of symmetry, and we will see that it should be generalized in some way. And the example that we will use is Maxwell theory. So we will also need to introduce gauge theory. That's the plan for today. But before that, yeah, just some more comments about this. The first comment that I realized I didn't make very explicitly last time is that if G is U1, so these are remarks. So if G is U1, which is the case that we used last time to introduce all of this, then a prominent role was played by the Noether current. And Noether current, as you can see, does not appear here, but it can be, of course, re-derived from there because it is essential to the symmetry. How do you re-derive it? Well, it's just you have a function or you correlators. The Noether current can be obtained by differentiation with respect to B. So the Noether current comes from functional derivative with respect to B1. B1 is a one form, so if you do this, you will get a one form. To be a bit more precise, it's very easy from the formula that I showed last time to derive something like if you have some correlator of whatever thing, if you hit it with, I think with my convention there was a minus I, B1, this correlator is computed in the background of the B1 background gauge field. So remember that means the path integral. That means the path integral over all the fields of the theory of E to minus S of the coupled theory, which depended on phi and B. That means that. And then you can check that this is the same as inserting the Noether current. So you have the same thing, and then you insert star J1. So that's a way that you can recover from that abstract definition. You can recover the Noether current just by taking derivative with respect to the background gauge field. That's one comment. Okay, since I'm discussing this, there was a question that I didn't really answer properly last time. Actually, Sylvain asked, and so I should just make it a bit more precise here. in the way that we find what is the coupled theory. So here I say it can be coupled. I don't say really how. I just say it can be coupled in such a way that the gauge symmetry is absolutely satisfied. The way we did it is, if you come from the standard way from U1, we did it by first computing, so we had a Lagrangian, and then from the Lagrangian we use Noether's procedure, so we obtain the Noether current, denoted J1, and then we said the coupled theory should be, so if you have phi and d, how do you couple? Well, you just take the previous action, and then you add a term, some I or something, minus I. I'm trying to be consistent with the sign and so on, but maybe I fail. So there was this, and that's what I wrote last time. So this was slightly incorrect. This is true only at first order in B. So here, when we do this J1, comes from using the fact that the symmetry is U1, so it's continuous. It's parameterized by a small parameter lambda, and that's what you get at first order. And so the statement is that this is what you have at first order in B. So plus terms which can involve higher powers in B. And then when we computed the variation of this, if you compute the variation with respect to lambda of J, that would be a term that is lambda B. So it's also second order in B and lambda. So yeah, that's why I neglected this term. And so maybe I can just write. And that's a slightly, it's important because at the end, there are some equations that are only first order, but then there are some which are absolutely exact. And I want to keep only the absolutely exact ones. The first order is allowed just because I have a U1, but U1 is a particular case. I don't want to depend on this. So the other equation we had was the variation. Well, how was the Noether current introduced? We had the variation with respect to lambda of the action. And this was I. Then we have this lambda. One, but that's also at first order in lambda, of course, plus. And so if you combine this and this, and if you combine with the gauge transformation of B, so the gauge transformation is B goes to B plus D lambda. And here this one is exact. There is no higher term, because that's the one we want to use for here. This is also exact. So if you combine this and this and this over here, you see that when you compute the variation of that, you might get higher terms, which depend on B squared, lambda squared, and so on. So, of the coupled thing here. You see that this term here vanishes with the other one, the minus I here. And so you get something of second order in lambda squared, B lambda, and B squared. And then it's not enough. So if you want to really find what is this action, well, then you have to repeat the thing to second order and so on to fix all the terms. And so in the particular case of the free field theory that I considered last time, if you do that, well, it's quite easy to see that the action that really has the full gauge symmetry is, but in a way, you transform the derivatives into covariant derivatives. So you have the integral of d phi minus b 1 like that, where star of the same thing. And now, when you have this, you see that there is a quadratic term in B that corrects the thing, which allows to have exact gauge. Okay, so that was one. This is the second remark, just to clarify this point. And then, so if there are questions about this, if you were not worried last time, then probably you don't really care. But
your approximation is 11 square. Only we stop at 11 square.
No. This is it can have any. In this particular case, yes, because it's a free theory, so the action is quadratic, and so yes, you could add a potential. Yeah. And so the other thing that we saw that I wanted to comment on, I didn't have time to mention it, is another hallmark of symmetry in standard QFT is word identities. So I just wanted to comment that this it also follows from that. So how do you do this? Well, assume, so I will do it in a very simple case. Assume that you have an operator somewhere here, O, and it has, say, some charge n with respect to the U1 symmetry. So this is still in the case of U1. Then we have, so I will try to draw in red the topological, the symmetry operators. So this is UG. And as we saw, when you have the operator, it implements the symmetry, say, in the interior. So then if you slide it across O, then it acts with the symmetry on O. This is what we derived last time. So that's the same. Now you have, so if O had charge n, it means that G acts on O with the n power. So you have G to the n, O, and then the operator can be put here. And then this you can contract to nothing. It's just G to the n and O. And all these equations are always valid within correlation functions. Okay, and now let's take, to derive the word identities, you write G equals to EI alpha. And then you take this equation, you send the circle here to infinity. So here I've sent it, in a way here I've shrunk on O, but I can also expand on the other way. So then I would just have O on this side. And then the thing acts very, very far. You don't see it anymore, but you can write the correlation function. You send the circle to infinity, and then you take the derivative with respect to alpha of the correlator that you get. It depends on alpha on both sides. Here explicitly because of the G here, which so there will be an I n alpha, I n which comes out, and then from here you will also get some term. Maybe I can just write it. So this equation becomes phi e to the minus s e to the I alpha integral over the surface of star J1. That's this side, and then O. So this is what this picture is supposed to mean. And then what we showed is that this is the same as this, G to the n. Same thing. E to the I n alpha O.
Where is n in the left hand side?
In the left hand side, well, it's not. It's hidden in the fact that we know that O transform with charge n. That's the point. So that, okay, let me derive it to the n, and then you'll see that on one side we will have n, on the other side we don't have n. It's another way of saying the symmetry. Okay, you can say where is n here? It's in what is O. So if you do this procedure, so here you take the derivative with respect to alpha, you see that this thing is brought down. Here there is an n, and then what you get is you just get this integrated G alpha on all of m, the integrated thing. I integrated by parts, so you see if sigma now goes to infinity, now sigma is the boundary of m, and then I use Stokes, the boundary at here. And then I have O, say inserted at a particular point x, and that's just n background 0. I put 0 here to say with respect to this notation here that B is 0. So that's the integrated Wall identities, and if you want, you can take the differential form of that. So you just take then it becomes that. So this is evaluated at the point y times O of x is just n times the delta function x minus y over 1. So yes, here you can ask again where is n, but it's not that it's just in the fact that this equation says that O transforms. So that's the more usual form of the Wall identity written as when points become coincident. There is a contact. Okay, and is there anything else I wanted to say? Yeah, there's a last comment I wanted to make with respect to last time's statement, which is it's an almost trivial comment. Maybe I don't even have to write it. If you take d equals to 1, so you take a one-dimensional QFT. So one-dimensional QFT is just quantum mechanics. It's just time. Now, what this statement means, now a codimension 1 operator in one dimension is just a point. So this thing tells you that in quantum mechanics, a symmetry means that there exist topological operators which are local. So they are points, but so they are just evaluated at a certain moment in time. So I could call them U of t, U G of t. And then the fact that they are topological means that I can move them in time freely, and I don't change correlators. But what moves in time, the generator of translations in time, is the Hamiltonian. So what the topological condition here becomes, it commutes with the Hamiltonian. So this statement for d equals to 1 means there exists a bunch of operators UG, which depends only on time. If you do two right after the other, then it's the same as doing the GG prime, and they commute with the Hamiltonian. And that's indeed the notion of symmetry that we learn. So just something also to make contact with things that we know. Okay, any question with respect to these things? There is the last comment, an important one. Here, I commented on the fact that there is a procedure that gives you, if you iterate this order by order, it gives you an action here, which is invariant, which has this symmetry. But this procedure is not unique. I could add any term here, or here, I could add any term which involves only dB. So for instance, if I want to add dB1 with star dB, for instance, it's of course still correct because that's completely invariant under any gauge transformation anyway. So it doesn't talk to the other fields, but it's there and I can do it. So the procedure is not unique. It can be coupled, but in many, many ways. Yeah, so we will also use this. Okay, I think now I've mentioned all the remarks I wanted to make about this statement. And now we begin with our exploration. So spoiler is today we will start modifying this by adding, we will be concerned about this codimension assumption. It sounds a bit weird. Why can we insert operators only in codimension 1? Well, we will see that we don't have. But I want to motivate this motivate it with a particular example. Again, I always try to find what is the simplest example that has the feature I want to show. So the theory that we will be looking at now, before moving to Maxwell, is a simpler one. It's just still a free scalar field, real, but this time a periodic one. And we'll see that the periodicity has a lot of consequences. One way of seeing it is, maybe I erase that. last time we considered the complex scalar fields, and we had the symmetry, which was rotating the phase of the complex scalar field. So today, I do something even simpler. I look only at the phase. So, first I wanted to use a different notation. I wanted to use theta for the field, but then it was a bit annoying, so I used still phi. But phi, you should now think of as a phase. So now, so that's compact real. So this will occupy us for until the break. Okay, so what is my fundamental field is phi. I still put this subscript 0. Still a bit heavy and annoying to carry those indices, but you will see that it will soon become quite useful to keep track of the indices. So phi 0, it's a scalar, it's a real, and I take the action. Well, so first, what is compact mean? It means that this will be identified with phi 0 plus 2 pi. And the goal is to understand what are the consequences of this identification. So I have such a field like that. If we write this in terms of normal fields in quantum field theory fields, if you want to write an action which looks like integral of d phi with star d phi, that's the kind of free action that you might want to write. You want the action to be dimensionless because you want to put it in the exponential. So if phi has dimension of a length, then that works. But that would be incompatible with that. So for that reason, you can imagine that if you want that phi is actually the same as phi plus 2 pi r. So it is a coordinate in the target space, which is a circle of radius r. But then since I don't want to carry these r's everywhere, I just rescale the field by r everywhere. So here I have to put an r squared in front of the action. There's an r squared, which is just a coupling constant. And at the moment, it doesn't really play any role. Later, it will be important. Then, in principle, when you have a complex field, you just write this. When it's real, you don't want to overcount degrees of freedom, so you put a 1/2. So I would like to put a 2 here. But then, because this model, as we will see, has some very nice duality properties, some kind of Fourier transform, and in Fourier transform, there are always 2 pi factors floating around. So I also want to add a 1/2 pi. So combined with the 2, it becomes 4 pi. Okay, so that's our action. So we study this, and there's this identification. Now this thing, because we are trying to make a framework to deal with symmetries and gauge redundancies and gauge symmetries and so on, I would like to rephrase everything in that language. So here, this you can see as a gauge redundancy. D phi, in this formula, I interpret phi as a real number. I didn't say that it's real. It's a real number, but it has this redundancy. It's not a symmetry of the theory. There is no, if we go back to our definition of symmetry, there is no operator that implements that symmetry. There is no way to couple to background field that implements this. It's just a redundancy. It's just that if I take phi and I take phi plus 2 pi, it's the same thing. So if I do the path integral, when I do the path integral, e to the minus f, what I sum over is not all functions from the manifold to R. It's all those which up to that identification. That's a prescription in the path integral. At the moment, this statement sounds very. Okay, so this is the scalar here. And if I want to be a bit heavy and insist again on that, you could say, okay, but how do you actually define, like, what is this object? Well, one way of answering is to say that phi is actually not a function from R. So interpretation. One way is to say, oh, actually phi is it's a function from M. So M is my manifold, MD, d-dimensional manifold, to well, to not R, but to R mod 2 pi z. This is exactly what this says. And this, up to changing addition to multiplication, is the same as U1. Right, so that's one possible interpretation. Another one is you could say, okay, I don't want to, like, I don't know what U1 is because it's too complicated for me. So hopefully it's not, but we will see later that when we go to higher degree, it will be this. We will need something to replace that. But then you can be more basic and to say, well, actually, okay, I can take my manifold and I can take a bunch of open sets, UI, UJ, and so on. And then each of them should be topologically trivial, so contractible. And also all the intersections should be topologically trivial, so contractible. If I have this, then I can just say, well, on each of those patches, because they are topologically trivial, I can just define phi 0 as a function from whatever open set to R. And then when I go from one patch to the other, I might use that. So I might change. So I might define it as this. And then on every intersection, if Ui, Uj is non-zero, I should have that phi I minus phi j is 2 pi times some integer, nij. Nij, some integer. This is not yet completely enough because I need to be sure that this is consistent. And if I have a triple overlap like this, and if I have defined Nij here, here, and here, you want the thing to be consistent. So you want the sum of the Nij to be 0. So you also want that if Ui, Uj, Uk is non-zero, you want to have Nij plus Njk plus Nki equal to 0. Okay, so the set of all this data, so all the phi, all the n's satisfying this constraint, that's a field. So you see, you have two equivalent ways of defining what it means to have a phi which is 2 pi identified like this, either this up here or this up here. Two color. Put this one in blue, and the other one so already here, even though that's more hands down, you see that it's a bit more cumbersome to work with. We have to carry out all these indices. That's more. So let's keep this in mind for this. Okay, so very simple theory. Any question so far? Okay, so now can someone tell me a symmetry of that theory? So we said this is not a symmetry. That's the gauge redundancy. What's a symmetry of that theory? One. Yeah, but tell me, how does it act? What should I do to the field? What transformation of this field leaves this invariant? Very, very simple. Yeah, constant shift symmetry. Yeah, exactly. So what are the symmetries? There is a shift symmetry. Phi goes to phi plus constant. Constant means constant over space. Of course, if I start doing adding something which is not a constant, because the derivatives not a symmetry. But okay, and that's, and it should be obvious because that's what we studied last time. I said this is just the phase of the complex field, and we are just rotating the phase, so now we are just shifting like this. So that's the symmetry. So okay, so now we're used to this. That's a continuous thing. This is valued in R. But is this really valued in R? Well, no, because if I shift by 2 pi, I can use my gauge redundancy to remove it. So actually that parameter is valued in R mod 2 pi t. So indeed the symmetry is not just R, what it would be if I didn't have this, but it's the U1, or it's that. I will constantly say that this is U1, because it's the additive or multiplicative one. So there is a U1 symmetry. And let's put the subscript m coming from string theory, or when you study the contract boson. This is the momentum symmetry. That's U1 m. Now, okay, we can run the machine, compute the Nutter current, which you compute it. So Jm is the one form, and it is just with the right normalization, with the Nutter, and you find this. Very easy. And now you can, I erased it, but now you can couple to background gauge field. So how do you couple to background gauge field? Well, you take this. Now the background gauge field is the n for momentum. This is symmetry. I have n's everywhere. And well, what is this? Now it have the gauge symmetry, so it means that you can shift with an arbitrary function of space-time and B absorb it. And is here. So clearly d phi minus b1. That's the coupled action. You see it involves a quadratic term in D1, exactly as I presented before, and nothing more. If you want, you can add anything depending on dB if you like, but okay, this is the minimal one. And you can check that the linear order in D is the Nutter. Okay. So that's the coupled theory. And now from there, we can run again the same thing as last time, and we can derive what are the operators that generate this. I won't do detail. There is the charge Q m, which depends on the d minus one dimensional manifold, which is just the integral of j on this thing. And then you have the operator u g. Okay, so now I don't have enough room for the indices. M g. It is just e to the I alpha times q. With g equals e to the I. Okay, standard thing. So let's try to understand what this does physically. What it does physically is we have the field. So we have, okay, so those things are, okay, I will try to draw with d equal to 3, for instance. I draw with d equal to 3, then the topological operator is some kind of surface. That's UG. And then it acts on charge fields. What are the charge fields? Well, they are the exponential of I with an n. So if I take this operator here at a point, that's clearly an eigenvalue of the symmetry. So if I move this across, or equivalently, I could circle this with a sphere. It's the same thing as putting my operator here, e to the I and I, and then putting a big sphere, d minus 1 sphere around, and then I shrink it, and I get the action of the symmetry, and the action is charge n, so I get n times the initial operator. That's how it acts in any dimension. Okay. So there you go. That's now. Yeah.
Should this be the action of Q charge instead of U?
Q. I think it should be U.
To be consistent, it should be like G to the N, right? Which is what
G
you
to the
want.
n, yes. Oh, you mean here I should put G to the n. Yeah, sorry. Yeah, you're right. E. So what is G? I didn't say what is G. Yes, G to the n. Very good. Yes, thank you. Yeah. So I'm just saying that if I act with G to this thing, this has charge n, so then I have a G to the n. Now, now the reason we're doing all this is because that's not all there is. There is another symmetry. And to see it, let's take d equal to 2 for 1 minute. So if we take d equal to 2, I claim that there is another symmetry. What is the other symmetry? Okay, so the other symmetry will be U1, and so we can find it by finding a conserved current using Nutter's procedure again. And so here you see I've used this. Yeah, I didn't check that this is conserved, but the reason this is conserved, so we have d star j1 equals 0. That's when we use the equation of motion to get this. And last time we showed that when you have the equation of motion, the current is conserved. But there is more. If you are in 2 dimensions, there is another one form which is conserved. I can define J, and then I call it W for winding. So what is this? It's 1 over 2 pi times star of d phi. So now it's really crucial that we are in d equal to 2, because in d equal to 2, that's a 1 form, and the star of the 1 form is a 1 form again, so that's indeed a current. And the conservation is trivial because, well, it's just d squared. We have a conserved current for free, only in d equals 2. But okay, let's see what it acts on. So we can do exactly the same as before. So we can define a Q winding, which is defined on sigma 1, codimension 1. We are in d equal to 2, equal with the same thing. It's just 1 over 2 pi, integral of star of d phi, so that's just d phi. But that's the charge. And you see why it's called winding, because if the phase winds around the cycle, then you pick up whatever it does. And now here we have our first little paradox. Again, here it's very, very trivial, but the first little paradox is that sigma 1 is supposed to be closed. But then if you integrate d something over a closed thing, you're supposed to say, that's the integral of phi over the boundary, but it's 0, so then that should be always 0. But it's not the case, not 0. Why? Because phi is not a real valued function. There is the identification. It's a more complicated object. So this notation is a bit tricky. We need to be careful about this notation, because if we are too careless, we might say, integral of d of phi is the integral of phi over the boundary, and then we get 0. But that's not the case. So all these things with d phi, they should be, we should be only locally it equals. We'll come back to this fact also later. But okay, so here it's quite clear what's happening. We can have a situation where we are in 2 dimensions. We have some kind of surface, and then maybe we have maybe that's our manifold, ND, which is N2 in this case. And then maybe the field phi does something like this, like it turns around. And so then when you pick this cycle, sigma 1, if you integrate d phi over this, you pick by how much it winds around this. And then if we want to do something similar to here, you want to shrink this thing, this is topological, until it hits something, the thing that is charged. So what is it that is charged? You see, it's the boundary condition. The boundary condition, I try to write maybe in blue the charged things. The boundary condition here is charged. This boundary condition, you can also think of it as, you can shrink it to a point, and then that would be a singularity. So you if you want, you can also draw this as, you take R2, but you remove a point. Here there's a blue point, which is this boundary condition here, which is shrunk to a point. And then at this point, the field phi is not defined. Then maybe it's just circled around like this. Here I'm drawing an arrow for the orientation modulo 2 pi. It's a good drawing. And then I integrate over sigma 1, and I get the winding number. Maybe it winds 3 times. So you see the charged objects are very different from those things, which are just a function built up in the fields. They are singularities or boundary conditions at which the field behaves in a certain way. The charged object are boundary conditions on which, so if they are boundary conditions, so if it is resolved, then you can say, yeah, if I integrate over the boundary condition, well, I get some integer, n. This has to be an integer because of our identification. Or if you shrink this to a point, then what does this become? It just becomes a vertex operator, equivalently vertex operator. The vertex operator means I take my manifold M, and then I remove a point, and then now this inserts a boundary, and then I have to specify in the path integral, which is here. In this path integral, I have to specify that around this particular point, I impose that the monodromy, in a way, the integral of d phi should be n, the charge of the winding number of the vector. And that's why it's called the winding symmetry. Is this all clear? Okay, so then last step. Well, no, first of all, I should, before doing the last step, I should say here I have described the symmetry, this winding symmetry with the concept current. Here then I have given the topological operator interpretation. And then you always have these the two aspects in mind. There are always topological operators and the background gauge fields. So I should be able to couple my action to a background gauge field. In this case, the coupled action at first order, well, it's very easy because we have the current, so we just add the current to this. So we have S of phi 0 and V1 magnetic winding. The initial thing that I don't rewrite, plus, then let's put the sign right. I over 2 pi roll up this winding thing. And from here, if you want, you can, well, first of all, you can check that this is indeed invariant under background gauge transformation. The background gauge transformation, what does it do? Maybe I could contrast it with the other one here. Okay, the board organization now is a bit, yeah, I will write all of them here. So we have D M1, which is shifted to Bm1, D lambda, and 0. And then you see it should shift phi with lambda. Okay, that's the thing, and then you check that this is of course invariant. And then there's the other thing here, BW1 goes to BW1 plus D lambda W. So now there are two parameters. There's lambda n and lambda W, but lambda W doesn't do anything on phi. Doesn't do anything on phi, so this is invariant, and that thing is indeed invariant. Let's just check why. If you shift dW by d of dW, d lambda W, then you get d lambda wedge d phi, and now that's a total derivative. Now this is integrated on all of them. So it pushes the integrand, so the lambda wedge phi, to the boundary. And if M, so usually either we assume that M is closed, so it has no boundary, or we assume that all the fields decay enough at infinity, and then the action is indeed invariant. The safest thing is to assume that it's always closed, and if it's not closed, then you have these punctures where you impose some boundary conditions. Okay, so that's the background gauge field of the star. Okay. So, and I think you see that we have checked that this winding symmetry is indeed a symmetry because we satisfy our requirements. We can couple it to background gauge fields. We can have the topological. Okay, we should check that everything is topological and so on, but this is guaranteed by the current conservation. We have the charge, we have the operators, and we know what are the charge objects. So no one can complain that this is not a symmetry. But now, let's change D. Let's go back to arbitrary D. So what changes? Well, now, this is still a 1 form, but now star takes a 1 form to a D minus 1 form. So now this is not 1, this is D minus 1. Okay, but it's still conserved. Except that now, okay, so is this formula changing? This is not changing. This is still sigma 1 because we are still integrating the star of this, so it's still a 1 form. So that formula stays like this. Nothing changes here. Okay, this drawing changes. In which way does it change? Well, now M is not a 2 higher MD. Let's say that it's 3, for instance. It's a three-dimensional manifold, and our operator is still supported on sigma 1. It should measure the winding number of the field phi. And so what does it wind around? Now it's not just a boundary condition which is like this. It's see, I have to remove a whole tube. Like you have to assume that now this is 3-dimensional, so it's like a full kind of bottle thing, and the field phi winds around. So there is a string if we are in 2 dimensions, or if we are in 4 dimensions, this will be a surface around which the field winds. So this
I'm not sure that I understand this translation you did on the boundary condition of the chart.
okay.
Can you explain?
So which part? You mean the fact that the charge object?
Yes.
Oh, how is it?
How you take the string?
Yeah, imagine. Okay, maybe this drawing is not the best. Imagine you have R3 now, not 2 but 3, and you just have the field which winds. It's like a vortex, but in 3 dimensions. So then there must be a center, but now the center is dimension 1. That's the string.
I don't understand the connection with your charging was in the binary condition.
Well, it means that then if I write, okay, what does it mean to say I have an insertion here? I have an insertion of a field. I just take the path integral, I have the measure, and I multiply by the field. Now I do something very different. I say I still integrate just the exponential of the action, but I specify that I have removed the points, and the fields over which I sum are those such that the winding number around this removed string here are the prescribed charge. The string, or in general dimension, is a two-dimensional thing. So this is still correct, this sentence. Charge objects are still either boundary condition and we impose this, or vertex operators. That's correct, but now vertex, it should be understood that they are not inserted at points, but inserted along, I will call them gamma, d minus 2. D minus 2-dimensional. And this, you see, this still works, except that now the background gauge field that I need because I want this thing to still be preserved, or let's say I want this to still be preserved, that's a 1 form. So now here I need a d minus 1 form. So B is a d minus 1 form. Of course, when d equals 2, you recover. And now this is a d minus 1 form. And here as well. And now lambda is a d minus 2 form. When d equals 2, we had a scalar, but now we have this. But you see that apart from these d's that I've added everywhere, nothing changes. And so this, I think, is the cleanest way to motivate the fact that there is no way you could have called the preceding thing a symmetry, and this is not a symmetry. That is still a symmetry, because it has all these properties. I've just added some d's. Except that now I violate the definition I gave at the beginning, because you see for instance, the symmetry operators, they are inserted not along codimension 1 varieties, but along 1 dimension, not codimension 1. So that's what motivates the fact that the definition given at the beginning was actually not correct, was too restrictive, and we should at least include that thing in the definition of what symmetries are. Okay, is there something else that I wanted to say here? Yes, there is a little bit more about those deals, and then we'll have the break. But I want to say one more. But the goal of these lectures, in a way, they are more basic than some other lectures on these topics that you can find. But I'm trying to be as explicit as possible, and in particular, every single equation or drawing, because there will be more and more drawings, in principle should be can be checkable in an easy way, some easy algebra. And if you remember, the central point from last time to motivate how do we go from the background gauge field language to the defect operators. To do this, we use the fact that lambda, we could pick anything, and then we picked a heaviside theta function. And the remind that last time we picked lambda 0 equal to alpha times theta of the codimension 1 manifold. We picked this, we inserted it in the action, and then it produced the action of this codimension 1 operator. And okay, that was a quite clear thing to do because you want to act on one side and not on the other side. But now, what are we going to do if we have a sigma 1? How do we have a theta function, a heaviside function on a codimension more than 1 object? Right, so let's imagine, okay, so let me finish the sentence. So remind, so we picked this, and then this led to the operators UG of sigma d minus 1. We use the fact that d, we use this, so you can check the notes from last time. This was the delta, which was a 1 form. We use this in the integral to get UG. That was the central technical part. So now we want to do this, but we want to replace this d minus 1 to an arbitrary k. Well, the idea is, again, to state the problem, let's take again this example. Let's take d equal to 3. And then let's say that our sigma on which the thing is inserted is dimension 1. How do we define the theta function here? The answer is you have to pick. Okay, the hint was last time when I said, when we did it here, there was one ambiguity. The one ambiguity was we had to say that sigma was oriented, then we have to pick one side or the other side. We have to say on which side does it act. There was left or right, plus or minus. Now this ambiguity becomes a whole one sphere of ambiguities. And then if you are in more codimension, there would be a higher and higher sphere. The way to represent this ambiguity is to say, actually this sigma 1, I can consider that it is the boundary of a one more dimensional sheet. Let's call it sigma tilde 2. So sigma 1 is the boundary of this. And now I can define what it means to have a theta function. So I define this. So if I have sigma k, so a k-dimensional submanifold of MG, then we define theta of sigma k. So now this will be a d minus k minus 1 form, singular. Because it's a distribution, the way to define it is to say how does it act on the test functions. So because it's this degree, I have to multiply by a test function. Let's call it 5, k plus 1. Then what happens if I integrate this over md? Well, I get the integral over this extension, the green thing, k plus 1 of f. Maybe with a minus sign convention. So this way, you see, I can define what is a theta function. And you might complain, oh, but there is an ambiguity. Which sigma tilde should I pick? Maybe I have many possibilities. The point is, this should not matter in the end. It's just, as it didn't matter last time, whether we pick plus or minus on each side of sigma. But let me just show why this indeed does the job. Because now, if we apply this on so remember, the goal of all of this is to take lambda. So now we will take lambda. We will take lambda with the appropriate degree, which is that, and then we plug this theta thing, and then we integrate by parts, and then it transforms into a delta function, and then the delta function restricts to the integration over the right thing. So yeah, so let me do it just in this case, and then we have the break. So again, this is kind of a technical tool, but it's the needed translation in order to show that indeed all these drawings still make sense. And if you really want one day to check any of the equations, well, at some point you have to pick all the choices. In the end, nothing will depend on them, but maybe on the intermediate steps, things will depend on which sigma tool you pick and so on. But at the end,
sorry, Antoine, what's the exact statement? I mean, for each k, it exists a theta.
Yes,
such that this formula holds.
Wait, okay, so that's my definition of, that's the definition of what I mean by theta d minus k minus 1. So yeah, for each k, I have a distribution like this, which can eat this thing, it's a k-dimensional manifold, and it outputs a distribution. This distribution is such that when I integrate against a test function like this, I get this result. And the reason it's the right thing to do is because if I treat it with a derivative, if I take the integral of m of theta, let me not take all the degree, because d minus k minus 1 of sigma k, and now I do it with a derivative of something, say d lambda, because that's what we will want to do ultimately, d lambda k, by integration by parts. This is minus okay, I can do it in two ways. Either I use this formula, so this is minus integral over sigma tilde of d lambda k, and then now I can move the d here, and that's minus plus k plus 1 k of lambda. But on the other hand, I can also integrate by part here, put the d here, put the minus sign, d theta gives me delta, so then I get minus integral of m of delta d minus k of sigma k plus lambda. And that's the formula that we want. We want that when we integrate the delta function, we get this. And that's what we use in order to translate all the drawings into equations. So every time, so from now on, I will not write these things anymore. I will make only drawings because it becomes a bit painful. But if you want, you can always do that and translate every drawing into an equation and then put it on a computer. Whatever. Yeah, and so let me just illustrate where we are. So for instance, again, if I take d equal to 3, but you can imagine higher dimension, we have our sigma 1, on which we support our operator, the winding operator. And then let's say we have some of those strings floating around. Where is the blue chart? Have some of those strings floating around. Maybe there's one here, maybe there's one here, maybe there's one here. What do? Well, you first pick a sigma 2, which is such that sigma 1 is the boundary of it, my green thing here. Here, because sigma 1 is closed, you see I have a very natural choice. I can just pick this. So this is my sigma 2. Now those guys are the strings. So they are supported on this d-2 dimensional manifold. These are d-2 dimensional, d-2 dimensional, d-2. And okay, I won't do it on the board because it's a bit painful, but it's just those equations many times. If you put this in the path integral, you can check that what you end up with the putting a boundary condition which is trivial on the lines, on the strings that do not cross sigma 2, and putting a boundary condition on those, measuring the chart. Repeat that. Every of these blue strings is a specified boundary condition like singular string, and then the sigma 1 thing picks up, it adds up all the winding numbers of all the strings that cross the green slice. So this statement is the worthy version of what you would get if you plug lambda equals delta in this equation and use the symmetry. Okay, now we do the. Are there any questions on that? Now we're done. Yes, there's a question. Yes, sigma 2. Yes, you can deform. Yes, that's the point. So here, actually, this thing that it defines a homology class, and so yes, you can deform the sigma 2 tilde as you like. As you can see here, if you deform it, you will never change the linking number with the blue guys.
In this case, it's nice. And the left-hand side is a bit confusing because if I want to think of it as normal data function, one value on one side and the other value on the other side, but then they're connected. So it's like the torus that you gave last time.
Yes, that's right. So that's very good. So that's the local description here. Now, indeed, if we have a global description, then it might be that there is no way to connect a trivial configuration with one where there is this, as we showed with the torus last time. So then it means that indeed there is no, we are inserting a twisted boundary condition or something. So then it's just a different sector of the theory. So you, for instance, if you think of this as a topological defect, then you are in the twisted Hilbert space. But then every variation on top of that will be of that form. It's exactly the same story as last time. If you have non-trivial topology, you have, and in the end, again, I didn't repeat that, but the other statement that we had at the end was that if you want to gauge the symmetry, or equivalently, if you want to know what are all the possible actions of the symmetry, then you should sum over all the topologically distinct networks of those sigmas. So yes, there are many topologically distinct. Okay, so now we can have the break, and next time after the break, we now put all the indices by one step, and this is now just Maxwell theory for free. Convince you. So as we wait that everyone comes back, I had an interesting question during the break about checking the invariance of the theory under this background gauge transformation. And so the point is, if you plug this d lambda in here, it seems that the action is not invariant because you pick up a term which is the integral of d lambda wedge d phi, and well, that's just there. There's nothing that compensates it because phi does not transform. So what's the solution? So actually I wanted to just comment on this. The point is, and because I haven't been very, very precise about what this lambda is valued in, but if you want the thing to be consistent, you want lambda to also have the same identification with 2 pi. Well, you can see from here, for instance, that phi is to be identified with phi plus 2 pi, then lambda has to be identified with lambda plus 2 pi. Now you might ask, oh, but wait, the lambda W doesn't talk to phi, so maybe I don't have to impose it. But actually, I have to because of this argument I'm just gonna tell. So if you plug in b plus d lambda in here, then you get a term which is I over 2 pi integral of d lambda winding -2 wedge d phi. And then you might be worried that that gives a non-zero contribution, and that's true. But then remember that I never asked that the action be invariant. I asked that the partition function is. The partition function is the action. You put this in the exponential and you integrate. And so the question is, when you put e to the 2 pi, sorry, not 2 pi, e to the this, e to the minus I, blah, 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 is this 1? And the answer is yes, because if there is indeed a non-zero contribution, from here you will get a multiple of 2 pi, and from here as well. Again, how do I know that here as well? Well, I demand it because of this argument. So I demand that this transformation, the parameter is valued in modulo 2 pi. And then you see that there is 2 pi from here, there is 1 from here. So the resulting thing is exactly an I 2 pi times an integer, which gives 1. So the theory is indeed, the partition function is invariant, so this is a symmetry. Okay, and before moving to Maxwell, let me just summarize a little table, easy, but just to keep track of the thing. We have 2 symmetries. We have the U1 momentum. This is the first one we discussed. And then I will start now putting indices also in the groups to keep track of what kind of symmetries we have. We have a zero-form symmetry. So zero-form symmetries just means normal symmetry, the usual one, the one that I defined at the beginning. And then we have another symmetry, which is U1 winding. And we see that it is not a zero form, it is a higher form symmetry. It was a usual symmetry only in d equal to 2. So from here you can infer that this is a d minus 2 form symmetry. These 2 is 0, but then when higher d, okay, that's non-zero. And then for each of those symmetry, we had the symmetry, the topological symmetry operator. And okay, I will not rewrite the expressions, just that these were supported on sigma d minus 1, 4-dimension 1. This is the usual case, but those guys were supported on sigma 1-dimensional things. And then we have the charge object, charge operators. Here, remember, they were these exponentials of I phi, I n phi. So they are local, so they are supported on points. So I'll try to keep the notation that sigma is where the symmetry operators act, and then gamma are where the charge objects are. So this is of dimension 0, while here, these were these, in 2 dimensions, these were points, but then in 3 dimensions, they were strings and so on. So these are d minus 2 dimensional vertices. So that's the summary from that discussion. Okay. Now the claim is all this formalism. I did it in quite some detail because it applies verbatim to the more interesting case, which is a gauge theory, proper gauge theory. But I also said that this was secretly a gauge theory. The identification, the phi plus 2 pi, this I said is the gauge invariance. So we just have to move everything 1 degree higher. And we will see that if we want to do the same thing as this, but with one forms instead of 0 forms, this is immediately the full gauge invariance, gauge redundancy of Maxwell's field. So that's the second part today. So write the action. So the action depends, as I said, it's everything I wrote, but one form higher. So instead of a 0 form here, I have a 1 form now. Of course, I call it A. So my conventions, which are standard in this field, is that the lowercase letters are used to denote dynamical fields. So here I have a 1 form. Of course, you know that it is some kind of a gauge field. From gauge field. It's a dynamical gauge field. So I put a lowercase a as opposed to my uppercase b. Anyway, this you should think of it as a lowercase phi. Otherwise, I would have written. Okay, so that's the thing. Now we have a coupling constant. What plays the role of the r squared of before? Okay, it's conventional to not call it r squared, but 1 over e squared. And I have the 2 because it's the real of the 1. Otherwise, it's exactly the same. Okay. And then I have the path integral defined for the partition function that defines the path integral. I have to sum over all these things, a1 e to the minus s. I do it in Euclidean, again, it's a bit simpler. That's it. Now, question over what are we integrating? So in the previous example, we were integrating over not all fields, but all fields with the periodicity. In the same way here, we have a huge redundancy in this description, because if I shift a1 with an exact 0 form, then I get exactly the same thing here. The equation is the analog of the phi equivalent to phi plus 2 pi before, except that now lambda 0 is an arbitrary function from my spacetime manifold into what? Well, r mod 2 pi z. You won't think of it as u1 again. So okay, so if you remember, when I wrote the compact boson action before, I said, I think now it's erased, but I said you can describe it in 2 ways. There was one way which I said I liked. This was the blue box thing. This is nice because it was just to say that phi is a function from m to u1. And then there was the cumbersome version, which was, okay, we define patches, and then on intersection, there is a transition function, which is an integer, and so on. So here, exactly the same applies, except that the cumbersome version becomes more cumbersome. We don't want to use the cumbersome one, but just try to see what it would be, and then I will not do it. But so what is A1 exactly? Okay, now I want to take the opportunity of discussing Maxwell and so on to not just talk about generalized symmetries, which we will see they are there, but also I think it's interesting to just clarify some common misconceptions about just what is the gauge theory, what is a charge, what is what is A1, and so on. So what is A1 exactly? So the first answer, the convoluted way, would be to say, well, okay, the naive thing to say would be to say, okay, it's a one form. But then if we say it's a one form, then we will very quickly run into trouble. As you know, for instance, we could not have monopole background. This kind of this would not be allowed by having a globally well-defined one. So what one could say is, oh, it's locally a one form. So what does this mean? If you want to unpack what this really means, then you have to say again, we have you cover your space with a bunch of open sets, and then they should be all topologically trivial and all intersections, double, triple, etc., until the lowest dimension, all total, so a fine enough covering. And then you say A1, I can define it in the UI, and now that's a well-defined, that's an honest one form. And then whenever I have an intersection on UI intersected with uj, if it's non-empty, then I have to say that A1i minus A1j. Well, now I can use, so before it was using the 2 pi periodicity, now it's using this whole huge gauge redundancy. So this should be some lambda 0. Now this is a function depending on ij, defined on the double intersections. But now, of course, if I have 3 intersections, these things should be compatible. So, oh, sorry. Yeah, I used the gauge. Then on triple intersection, ui, uj, uk, it should be compatible. So then I should have something like lambda 0 ij plus lambda 0 jk plus lambda 0 ki equal. So before it was 0, but here because it's only d lambda and everything is valued up to 2 pi, now I could still have some integer times 2 pi. So I have to write 2 pi times n ijk. Well, now you see I have this integer with 3 indices. But now I need more consistency conditions because I have these ends and they should be compatible. So then on every 4 intersections, I should write, well, I leave it as an exercise to write exactly what it is. There is some combination of all the ends, which should be 0. So that's this whole bunch of data. That's what you should say when you say I have a one form. And well, in this course, we will then go higher later on. So this is not really the way you want to go. So that's the cumbersome way. So now let's try to give a non-cumbersome way. So in the previous case, the elegant way was saying, because we were clever and we know what U1 is, we just said, it's just a function into U1. So is there a way to say an equivalent thing? So, well, if you know differential geometry and so on, you can say, oh, actually A1 is a connection on a U1 line bundle over n. And okay, that's a well-defined thing, and indeed, that's what matters. Although you should also say that you should only take in what you sum over here, you should sum over isomorphism classes of those. So, so A1 is this, and so the path integral is over isomorphism of U1 line bundles with connection. So okay, that's a correct thing. And that's a bit the equivalent of the previous statement when I say it's just a function into U1. Now it's this complicated thing. But then I can ask the same question. What is if we want to do a theory of a two form, then it will be even more complicated. So we don't really want to use that either. And there is a very elegant answer to all these questions. And the goal is not to expand too much on that, but just to give a flavor. Because it's cool time. But there is an elegant answer. Again, for instance, the reason you can say this one is not too elegant is because it's really specified to A1. If you want to recover the previous thing, the I0, you cannot really express it in that language. So that language here will work for everything at once. So it's known as a figure assignment differential character. And if you want to have to read a physicist-friendly introduction to this, you can look at this paper by Fried, Moore, and Siegel, 0605. To explain here. I will just give you the definition, explain why this is indeed the thing that we want to do. And today we will not need too much of the technicalities, maybe we could come back a bit later. So what is this thing? It's a frightening name. You write the definition. Maybe it's frightening as well, I don't know, but then we will unpack it. So these groups of Giga Simons differential characters, they are denoted by H check. And the one which is relevant for us here is H2. So we have our manifold MD, and what is H2 of it? It's the set of characters. So what is a character? The character of a group is a function from a group to U1. So these are character. So they go from a certain group to U1, and they are group homomorphisms. Now from what? Well, the goal, okay, what's the intuition? The intuition is, what's the connection? Connection is a thing that tells you how to move on your bundle. You also have connection in GR and so on. So you have M, that's M, and you want a point, and you want to go on another point, and you want to transport your thing, you want to connect points. So that's a general connection. And the point is, the only thing that is important, because you have this huge gauge invariant, in the end, the only thing that matters is you can always change things here and here independently by using a lambda, which varies hugely between here and here. But what you cannot do is, if you go back to your initial point, now the thing should be gauge invariant. So that would be our Wilson loop, which could appear very soon. So the idea is, what matters is what is the holonomy that you pick up when you go along the loop. So the group here that we want to take as a source is Z1 of them. What is Z1? Z is the closed loops. Right, so when you last time I introduced the chains, and then there was these are the closed chains. So these are the chains without end. So because it's one chain, it's just a loop. So these are loops. Nothing to be frightened about. These are just loops. And there's a group of loops in them. It's kind of a formal group. You can add up loops, multiply those. So character is a thing that associates with every loop, associates a phase in U1. So it's a holonomy. What should that satisfy? I have to erase that. Let's look at this paper. Right? What is nice? Well, you want that these characters are such that there exists a two form F. I call it F because it's the curvature. F chi, so associated to everything, there is a two form. I insist that this is indeed a two form on M. It's globally well defined, no trick here. There is a two form such that for every, so as long as you have, as soon as you have a two cycle, so let's say you have a two chain, or a two-dimensional thing. As soon as you have this, then the holonomy should just be given by the integral of F, which is what you want. So as soon as you have a sigma 2 in C2 of n. So C2 are just the two chains, so just the two-dimensional things in n. Well, then chi evaluated on the boundary of sigma 2, that's now a one cycle, it's a certain phase. What is that phase? Is the exponential of I times the integral of f over sigma 2. Okay, so written like that, it's a bit it's a mouthful, but okay, it's just we're just saying that we want holonomies. They associate a value to every loop, and if the loop is the boundary of something two-dimensional, then the value is just given by the integral of f, which is given to you. Well-defined ever. The claim is that this is exactly what you have to sum over. No less, no more. You don't have to take equivalence classes and so on. That's the thing. That's what A is valued in. And because this is the geometric information that you want, like defining a one form is really, really too much. You don't want that because you have all the gauge invariants. It depends on too many things. The only thing that matters is what happens if you do a loop. And if you do a loop which is the boundary of something, then it's just the integral of f of some curvature. If it's not, then it can give something else. But of course, it's very strongly constrained by the fact that whenever it's a boundary, just mention. Is it clear the definition here?
Can you give an example with some?
Yeah. So let's do an example. So well, first of all, okay, let me say. So if chi is such a thing, then I'm given this f, and this is the two form, totally well defined. And moreover, because of this thing, you see, if I'm given this. Now, if I have a sigma 2 which has no boundary, I have a sigma 2 with no boundary, then what is chi evaluated on that? Well, this is 0. That's a group homomorphism, so it should give 1. So that's 1. But by this statement here is also the integral, the exponential of I times the integral of f2 over that thing. So what that means is that the integral of sigma 2 is quantized in units of 1 over. That's a super important equation. So the two form is actually has quantized flux. That would be interpreted as the magnetic flux. And yeah, actually, let me give now it's a concrete example. But yeah, let's make it very concrete. Let's take M to be the two. Let's compute H2 of the two sphere. Well, I don't want to be actually too long and to make the whole computation. The claim is here. How can it be described? Well, it's described as follows. You have one integer, which is the value of this, which is the monopole charge. So there is. Then let's make a picture of H2 of S2. There is H2 of S2 valued in Z. That's the second cohomology group, so that's just Z in this case. That's just the monopole number. You know that on the two sphere you can have monopole background, so that will give a value to this. This is an integer. Sorry, I didn't write this. Didn't finish my sentence. So that's the monopole number. And then for each monopole number, so that should be -1, 0, 1, 2, and so on. For each thing, you have a vector space, copy of a vector space, which are all the small variations that you can make on the monopole background. So you have a monopole background, and then it can still take many non-trivial values. This is an infinite dimensional vector. Actually, you can find it as the image of the spherical harmonics. But that's an infinite dimension. That's the copies of an infinite dimensional vector space of the spherical harmonics. That's what you have to sum over if you're doing path integral over S2, which means concretely you have to sum. There is a discrete sum over the monopole numbers, and then a continuous path integral over just modes of the vibration. And this is the normal integration that you do in QFT 101, the mode integral. So it gives typically an infinite determinant that you have to regularize and so on, but that's not how. So that's what it gives on S2. And actually, the general picture is not so much different. Again, if you're interested, you can we can discuss this later. I will just give the general picture for if the manifold is not S2. If it's a general manifold, then the story is yeah. Replace the horrible. Let's say I have a general ND closed simplicity to not have to deal with infinity. If you have this, then the picture is the same. So you have some kind of discrete. You have a discrete number of things. Those things will be labeled by this H2 of S of the manifold now, valued in Z. So this is called the characteristic class of A, or of character. It's called A, confusingly A. Let's call it C. So in this case, it was the Chern class. So the characteristic class. And then for each of these values, this is typically a discrete thing, it is in Z, so it's Z or maybe Z2 or something like that. And for each of them, you have the integral over all the modes, like this. So you have a copy of this everywhere. But let me focus now on the zero case. So zero is when the Chern class is trivial, or whatever this characteristic class is zero. Then what does it mean? When it's zero, it means that actually the one form is well defined. And you have a topologically trivial character. Then the one form, there is a well-defined one form A that you can find as the kernel. If you want to be a bit formal, you have this map that takes here and takes you into H2. And this map is not a bijection. It has a kernel, those which yield 0. The kernel can show that it's basically one forms. And then because of it's modulo one forms with integral period. And these things here, these are the connections. These are the A's. These are the A's that you properly define. So what this sector here is, above 0, these are the topologically trivial ties. And this is equivalent to having A1 well defined globally. Again, think of the monopole thing. If you have 0 monopole number, then A is well defined globally. And now, what is the structure of this? Well, on this vector space, you have a particular connection, which is the trivial one, which gives 1 always. To everything, you give 1. So no holonomic constant. Somewhere here. And then, but then let's assume that we are maybe on a torus or something. So there is a 1 cycle. So if you're on a torus, then you can integrate over a loop like this. And you see, it's not really constrained by that. The only thing that it's constraint is that this is an element of U1, so it's a kind of a number modulo 2 pi. So to each cycle, you should associate a number modulo 2 pi, which is the holonomy of that modulo 2 pi. And you do this for each cycle. So you and what is a number modulo 2 pi? It's a circle again. So there is and how many circles are there? Well, as many as the numbers of one cycles in your manifold. So above this point, there is a torus. This is a torus. This is S1 to the power of B1. B1 is the first Betti number, so just the number of one cycles that you have. And for each one cycle like that, you can have a phase modulo 2 pi, which is a circle, so that you have a torus like that. These are the torus of phases. And then this is valued over every point. And then that thing is the oscillators that I mentioned before. So that's the picture for the topologically triggered thing. And then if you want to move to other sectors, it's basically the same, but you have to add, like this becomes a time. This is the picture. So you have a copy of this everywhere. And so those guys here are the flat. It's just important. These are the flat connections. You see, they are flat because they are just given by the value of the holonomy around that. There is no vibration, nothing. Then if you move somewhere else, like here, you can also have the same torus. But now these guys are not flat because you've activated some oscillators. So the flat topologically triggered connections, the intersection of flat and topological, there it's this torus. Then when we want to gauge a symmetry, you have to sum over every flat connection. So not just this torus, but also the copies, which would be a bit twisted, which appear in the other sectors. So I don't know if this really makes it simpler, but I try to convince you that at least you don't have to take equivalencies and so on. And let me just say one more thing, and then we move on to Maxwell. This answer, I said, is valid for every dimension. So you see there are some twos and ones floating around everywhere. You can replace them by arbitrary p. Right, so this would be p, this would be p minus 1, p, 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 p. If you do that, and if you replace all the twos by ones and all the ones by zeros here, then you get something exactly the same definition. It gives you, this is an exercise, this is a simple one. It's just exactly the function from m to u1. Yeah, I can just do it to show you how easy it is. It's beautiful. I mean, they're very simple. I should not have erased that. So if you do the same thing with 1, then what it is? So what is h1? It's the set of chi's which are functions from Z0. What is Z0? It's a zero-dimensional subset of M. So it's the set of points. So each point, you associate what? An element of U1. So already we have that. And then what does it give? It tells you that there exists an F. There exists an F1, which is such that as soon as you have a one-dimensional sigma 1, then you see chi of this sigma. So let's say it goes from x to y. What is chi of this sigma? It's just chi of x divided by chi of y. It just tells you that this is the integral of f over the path here. Gamma of sigma 1 of f1. But that's no constraint at all, because whenever you have a function like this, you can always define an f which satisfies this. So yeah, if it satisfies this, which means it doesn't depend on the path. So yeah, there is no constraint. So actually, H1 is really just functions. And then you can try to make pictures to understand what is H3. For instance, if you know in string theory there is the B field. Sometimes you say the B field is a two form. It's the same. It's not really a two form. If you say it's a two form, then you will have problems when you integrate on the cycle. you integrate dv on a cycle, it will always give 0, but no, that's not. So B in string theory is just in H3. And all the fields, they are always in H3. Okay, so it took maybe too long on that. The point is, we should always be careful when we write dA. That was the point. We should be careful when we write dA, and so the constraint, if I erase, I rewrite it here, is this. And again, if you think that dA is a normal one form, that would be always 0, but no, you can have none. Okay. Any question on that part? Yes. Okay. Now we have 5 minutes left. So we will study the symmetries in more detail later. But I just rewrite the action. I just want to show the symmetries, but we did all the work already. That's the action. And now the symmetries, I just copy what I wrote for the compact scalar. You remember there was a J1, which was so there was r over 2 pi, and now there's just 1 over e squared times star times dA. Right? In the previous case, it was d5, but now it doesn't work. It has to be a 2 form. And then this is confirmed by the equation of motion. The equation of motion are just Maxwell's equations, and they tell you that d a1 equals 0. That's 1/2 of Maxwell's equations. The other half is the one that just say that d times d is locally 0. So even though dA1 is not really, even though A1 is not really a one form, it's still valid that d squared is 0. You can also check it in case. So you have another current, which is, and I put the same normalization as in the compact scalar. This was very important to have the 1 over 2 pi in order for the cancellation that I mentioned after the break arises. We want the action to really be invariant, so we need this 1 over 2 pi times star of d A1. Now let's fix the degree. A is a 1 form, D is a 2 form, star is D minus 2 form. So it's exactly like in the case before, but everything is 1. And before I call this momentum and this one binding, in this case we will call this electric and magnetic. Why do we do this? Well, because now we can compute the conserved charges. So we have a U1, so the symmetry, we have a U1 electric, so 1 form symmetry, times U1 magnetic. So what? Okay, so you remember how we do the thing. A P form symmetry has a P plus 1 form current. So that should be P plus 1. So the thing is D minus 3. The D minus 3 form symmetry here. And what are the charges? Well, the electric charge, QE, is defined now on a codimension 2. Again, I have not done yet the definition of higher form symmetries, but it's clear that we want to integrate the star of this, so it has to be codimension 2. So it's star of JE sigma. So it's just the integral of star dA. And then Q magnetic. Now it's defined on 2 dimension, not codimension 2, but 2. Okay, same thing. D minus 2. And that's 1 over 3 pi. Okay, and now very conveniently, that thing comes out to be quantized. So this charge is indeed quantized. And that charge is also quantized. That's what E means. In a way, we have to normalize the thing once, and then we cannot do it more. Where we normalize it is by saying that the charge of the fundamental electric excitations will be E. So we require that this is in Z, and this is also in Z. The fact that the charge is quantized means that we are in the gauge, the global symmetry is really U1, not R. Okay. Now, why is it called electric magnetic? I guess you know this, but I guess I have to write it at least once. If we do it in I just erase it, but to be quantized, we needed the surface to be closed. So the same holds here. This is if those things are closed. Otherwise, of course, you get only part of the electric flux. So let's just write. So for V equal to 4, standard Maxwell in 4 dimensions, then as you know, dA is now a 2 form. The field strength F2. We can write it, in a matrix form. You have Maxwell is when V equal to 4. We have this nice symmetry. And so star dA 1 and dA 1. Let's just write directly the answer. So QE of now sigma 2, but let's take it to be a sphere. To be simple, is just the integral over S2 of star in 3 dimensions of E, which is one form here. Or in more basic language, is the integral of S2 of E ds. It's the flux of the electric field. And Qn over S2 is the same thing, integral over S2 of the B field D2. I'm restricting to the space. Yeah, I didn't take it. Here I pick a spatial S2 here, and then if you translate the vectors and so on, okay. So electric flux, magnetic flux, that's what it measures. We have Gauss's theorem that this flux is equal to the integral of the charge contained inside the S2. Now, this is for spatial S2. I just want to describe what are the charge operators. Similarly to this little table that I put at the end of the first part. Give this nice picture. So we have the electric, the one, it's a one-form symmetry, and we have the magnetic, the one, it's the D minus 3 form symmetry. So we have the symmetry topological operators, which are supported in dimension D minus 2 operators. And if you go back to the table before, well, also it's clear from the linking, what this measures is the charge linked by that. So the sum of the dimensions of the things you put here and here should be D minus 1. So here it should be 1, and here it should be D minus 3. So they are supported on this kind of manifolds. If D equal to 4, you see that this is also gamma 1. So they are both supported on strings. What are these? These are the Wilson lines. Maybe I'll do it next time. Let me just write the definition. Wn, depending on gamma 1, is exponential of I times the integral over gamma 1 of A. So next time we will discuss why this is with n. n is the charge, and n has to be an integer. So next time, maybe I'll discuss again why this is quantized and so on. And those guys here are, so if you remember in the case of the compact boson, those guys were the particles, the insertions, so that's what takes the place of them. And now those were these defects, vortex strings. Well, now these are monopole, whatever dimension we are in. So if we're in 4 dimensions, they are also monopole lines or sloped lines with d equal to 4. Say one more thing. So now basically I'm done. I just wanted to make a comment of my personal take on this. When I studied electromagnetism, or maybe yes, electromagnetism, but so first you learn electromagnetism, right, in the first year. And then a few years later, you do quantum field theory, and then you learn about symmetries and Noether's theorem and so on. And then they always tell you, you have a symmetry, and then you have to integrate the charge. It's always the integrate over all of space. So integral over R3. That's what you read in the textbook. And I was always confused because it doesn't match with that. You see that if you want to, in first year of electromagnetism, you learn that the charge is obtained by integrating over a sphere. And then you have the electrons in the middle, and then you integrate the flux over a sphere, not over a 3 manifold. So there is a mismatch of dimension. And in a way, that's what triggered also this whole rephrasing. It's just the fact that what we call symmetries in quantum field theory, at least the definition I gave at the beginning, just doesn't match with this conserved charge in Maxwell. So, but this is where charge comes from. When you think of charge, you think of the electric charge. So the archetypical example of a charge does not fit the definition of the charge that we usually give. So there is this mismatch, and it's a bit weird that no one really did something, earlier than that, earlier than 10 years ago. But
when you usually, when you say the what usually is with quantization or without?
Yeah, with quantization, like if you, I don't know, classical, take an electron.
Quantization with relativity are there similar?
But it doesn't, I don't think it changes anything. Like in this, okay, I can really, okay, let me make one last drawing. Take a Wilson line in 4 dimensions, but now the Wilson line, take it at constant position in space. It extends only in time. So a Wilson line is what? Is a very heavy electron in the city. Should be in blue. There's an electron sitting here in space, and then you are integrating over a 2-sphere the flux. That's all we're doing. And you have to integrate over a 2-sphere. You cannot get the electric charge if you integrate over a 3 manifold as you're instructed in by the standard symmetry recipe. So anyway, this is nothing really deep. But it's something to, if you remember one thing out of all of this, it's that there is a mismatch. That the charge, the electric charge of Maxwell is not agreeing with the charge given by Noether theorem and so on. If you want to have agreement, you have to generalize the notion. So that's why this story of the generalized symmetry is so natural, because even the simplest examples are already generalized symmetries. Nothing exotic. Most basic. And I will try to illustrate more with more very, very simple theories later on, and we'll discuss how those things are linking anomalies next time. So thank you. More questions about?
Not yet. No, it's quite confusing, the last point you made.
Even about the charges?
Yeah, the charge operators, why can't I think about electrons and monopoles? You're basically saying that we shouldn't think about electrons as objects.
Yes, electrons, they live in time. They are one-dimensional objects. You never measure the charge of the insertion of the electron field. If you write QED, you have psi of x and so on. You never measure the charge of psi of x. That you would integrate over a 3-sphere, but you don't do that. That's not even allowed. It's not gauge invariant. It doesn't work. what you measure is the charge of the Wilson line, of a one-dimensional thing, and you link it with a two-dimensional sphere, and that's Gauss' theorem. There's no way you could do it, of course, in the previous example, in the compact boson. Then yes, you have these field insertions, these exponentiated e to the I n phi, or the vortices in two dimensions. They are fine. They are usual symmetries. But the charge in Maxwell theory are not. They are generalized charges, generalized symmetries.
The construction you gave for the space of the one form A1, does this generalize it to non-abelian sheets, non-abelian gauge groups?
No, yeah, that's a good question. So in the
I forgot the name of it.
Yes. So in the definition, there was so chi was defined on the Z1 or whatever, Z1 to U1. You might think, oh, let's replace this U1 by some other group, and then I have defined it. So that doesn't work so easily, because then, remember, there was the other equation, chi of the sigma equals e to the I exponential of I integral of s. That is really a complex number. So you would need to find a generalization of that. So I don't know a generalization. Maybe there is one. What you can do is to take any subgroup of U1. So actually, we will do it with Zn. So I think next time we will need to consider some TQFTs, which are Zn H series, and then you have to sum over Zn connections. But again, that works because it's a subgroup of U1. If you wanted to do, and it's nice that all the abelian finite groups are products of those. You could put also, of course, several powers here. But if you want to do non-abelian, I don't know how to do it. But as we will also see very, very soon, all these higher form symmetries are all abelian. Yes.
For non-abelian group, the holonomial group depends on where you put the sum. So that's the conjugate.
Yes. No, but you take the trace. Yeah, I think you would take the trace, but
Could work for loops and not for high dimensional.
Yeah.
But as you said, they would be abelian.
Okay, so if there are no more urgent questions, we thank Antoine.